Good morning. We begin lecture 8. We will do an example first, just to sort of refresh our understanding. It is probably an example that is similar to what you have done in the assignment sheet, but I thought it will be interesting for us to discuss it, especially since we have spent a fair amount of time discussing sampling and reconstruction. And what we are going to take away from this example is our understanding that when we change the sampling rate, there are some things that we have to be very careful about, and that is what I hope today's example will help us. Now, this is a block diagram that you are familiar with. This is when we do discrete time processing of continuous time signals. One very key element that is in this figure, which enables us to get the linear time invariant system for the continuous time system, is that you have the following. You have Ts and you have Ts. Okay. The same sampling period that you have used at the input is what produces at the output, because if you have different sampling periods, then you will lose the property of linearity. Okay. So, we are deliberately going to violate that and see what is the impact, and that is the purpose of this first example. So, very quickly I am going to use a sampling period T1 and a sampling period T2. Again, they can be equal, they may not be equal. So, this is the and we will assume the following, that in the C to D converter there is an ideal anti-aliasing filter. So, that means it will not allow aliasing provided I have satisfied Nyquist criterion. And in this block, the D to C block, I have an ideal reconstruction filter. Those are assumptions that we will make, and we will see why those were important and what sort of insight that it gives. So, I do not want to bring in any effects of filtering, practical filtering. Assume that ideal reconstruction filter. The both ends we have ideal filters that are present, that means they are brick wall filters. Okay. So, here is the problem statement. I have a signal which is band limited. It is band limited to 2 pi times 5000 hertz, okay, 10,000 pi radians per second. So, this is minus 2 pi times 5000. It is a band limited signal. So, and the discrete time system is a low pass filter with minus pi by 2 to pi by 2 cutoff. Okay. And basically this is xc of j omega magnitude response, h magnitude h e of j omega. This is the magnitude response of the discrete time filter. Okay. So, keep this picture in mind. I have to shift over to the next screen and continue the example. So, the task is to sketch y r of j omega magnitude under the different cases that we will have to work with. The first one is probably a very straightforward one, where we say that T1 equal to T2 equal to 1 by 10,000. Okay. I have up to 5000 hertz. I am doing a 10 kilohertz sampling, a reconstruction at 10 kilohertz. So, therefore, there is a ideal anti-aliasing filter. So, no aliasing, and then the reconstruction filter does the perfect job for me. So, just draw the sketch of the output spectrum. Let me draw the output spectrum and just make sure that you are comfortable with that. If there is a doubt, we will answer it, otherwise we will move on from there. So, the output spectrum, because it passed through a low pass filter, will have the following shape. It will basically, some portion of its spectrum would have been removed by the low pass filter, okay, and the cutoff frequencies would be, it would have been pi by 2 in the discrete time domain. So, pi by 2 in the discrete time domain, and the continuous time frequency would be this divided by Ts 1 by T2, and this would be 2 pi times 2500. So, some portion of the spectrum got removed. This in the continuous time, this is 2 pi times 2500. This is omega axis, this is yr of j omega. Okay. And any scaling of the spectrum? Any scaling of the spectrum? I would have gotten a 1 over T1 when I did the sampling. I got a T2 when I got the reconstruction, T1 equal to T2. So, therefore, this is equal to 1. Okay. No scaling of the spectrum. Okay. The first interesting case comes now when I have T1 equal to 1 by 20,000 and T2 equal to 1 by 10,000. It is a multi-rate system. Basically, I have deliberately introduced a sampling rate change. Just want to get a feel for what is happening in terms of the continuous time signal. Again, this is more of an example just to explore and develop the insights. Okay. So, first step is what is the discrete time spectrum. Discrete time spectrum says I have signal up to 5000 hertz, I have sampled it at 20,000 hertz. Basically, the spectral content is from minus 5000 to 5000. I have sampled it at 20,000 kilohertz. So, 20,000 kilohertz approximately is 2 pi. So, if I were to look at 5000, that becomes 2 pi by 4. So, basically this would map to pi by 2. So, this corresponds to pi by 2, this is pi, 3 pi by 2 and 2 pi, and this is the next copy of the spectrum. So, this is the discrete time spectrum of x of E of j omega. Okay. Now, this went through a discrete time system with the low pass filter, which was a low pass filter which was going from minus pi by 2 to pi by 2. Notice that it did not do anything to the spectrum. Basically, the spectrum went through and then it is passed on to the reconstruction filter. The reconstruction filter, as before, does the reconstruction process, removing the spectrum. So, this time around the entire signal seems to have appeared on the output. So, the discrete time frequency is pi by 2 and I have to convert it into a continuous time frequency. So, into 1 over T2. So, when I do this, this becomes 2 pi T2 is 10,000. So, it becomes 2 pi times 2500. Okay. So, this becomes 2 pi times 2500. Now, what happened? I gave a signal which was up to 5000 hertz. It got digitized, sampled, it went through a low pass filter and then came out, and I reconstructed it, and looks like everything was there as before, except that there has been a scaling or a warping of my frequency axis. Okay. Now, this is a very important element. If we do not have the same sampling rate at both ends, there will be some kind of a warping of the spectrum. Either you can have a stretching or you can have a compression, and in this case it turns out to be that the frequencies looks like it got compressed, and this is typically what happens if you sample at one rate and play back at another rate. There will be some warping of the spectrum. Now, is there any scaling? So, there is a 1 over T1 scaling at the sampling point, and then there is a T2 by T1 part, and T2 is 2 times the because T2 is 1 by 10,000. So, this would be equal to a factor of 2. So, I got a scale factor of 2 and then a spectrum, but and the axis on the spectrum is not what I sent in at the input, but this is a result of the warping that has happened. Okay, just one more variant of this, and we will conclude this. The part C, this one, the input sampling rate is Nyquist 10,000, output sampling period is 1 by 20,000. So, the reverse scenario. And of course, if I sample it at Nyquist rate, the low pass filter will remove some portion of the spectrum. So, the output spectrum is going to look as follows. It is going to have this shape, okay, and in the discrete time this cutoff point was pi by 2, the continuous time frequency was omega into 1 over T2. So, this will come out to be 2 pi times 5000. Okay. So, this spectrum, I do not need to do a dashed line, I will just use a solid line, is 2 pi times 5000, this is minus 2 pi times 5000. Okay. So, again another sort of interesting outcome from this example is that the filtering did happen. The low pass filter actually removed some portion of the spectrum. I passed it to the reconstruction, but because my reconstruction assumes a different sampling rate, my frequency axis is now actually distorted, and the interpretation comes out saying that, hey, you have frequencies all the way from minus 5000 hertz to plus 5000 hertz, which is not correct, because I have it is, the interpretation is correct, however that was not the intent, because when I passed the signal through, I wanted to remove some portion of the spectrum. So again, keep in mind that the sampling rate plays an important role. It is something that always, oh, by the way, this will have a scale factor of 1/2. So, and this would be mod y reconstructed of j omega. Okay. And it is some very interesting things, and these can actually be leveraged into our advantage whenever there is a requirement, and so the flexibility of the sampling period is something that we want to keep in mind always. So now I will spend a minute or so on the review of yesterday's lecture. So the primary contribution of yesterday's lecture was the upsampler or the sampling rate expander, and the notation that we have is a box with a up arrow, upward pointing arrow, and an integer L, basically, which means that I am doing an increase by an integer sampling factor L, and the if this is x of n, this is x e of n expanded version, we wrote down the time domain relationship, x e of n is x of n by L if n equal to a multiple of L, 0 otherwise. Okay, that is the time domain relationship, and we also derived that x e of z is x of z power L. We said that this basically introduces L minus 1 copies of the spectrum, L minus 1 copies of the input spectrum. There is also a scaling of the frequency axis, because x e of j omega, the period for this one is 2 pi, and for x e power j omega L, the period is 2 pi divided by L. So basically in the range 0 to 2 pi you will have L copies of the spectrum, 1 original copy and L minus 1 additional copies. Okay. So this is the general case, that the new periodicity, and from this we can derive. Now the interesting observations about this are twofold. The first one is whether the system satisfies linearity and time invariance. So the question is, I have the upsampler block, upsampling by a factor of L, and this is x of n, this is x e of n. Now the question is whether it satisfies linearity. If I scale the input, output will get scaled, so there is no issue about that. If I add 2 signals, the output will be the sum of those 2 signals with the appropriate zeros inserted. So linearity is very straightforward for us to verify. Okay. Now the time invariance property, probably easy to see, but also need to be careful to show it in a more systematic fashion. So if I have an sequence 3 1 2 with this being my origin, and I pass it through an upsampler by a factor of 3. Okay, if I pass it through an upsampler, so the new sequence becomes 3 0 0 1 0 comma 0 comma 2 comma dot dot dot. My origin remains the same, does not change, but I have inserted the zeros. So this is x e of n. Am I right? I have inserted 2 zeros between every set of samples that I have at the input. Now if I want to delay my input by 1 unit of time, I apply this, then the sequence that I get at the other side will be 3, 0, 0, 1, 0, 0, 2 dot with this being my origin, right, if I shifted my input by 1 unit of time. Okay. Now, clearly that is not the same as shifting the output by 1 unit of time, because if I shifted the output by 1 unit of time, it would point to that direction. So, shifting the input does not produce the same shift on the output side. Again, it is something that is probably obvious that you can, but be careful. I mean, also just be comfortable to be able to show that yes, linearity holds, the shift invariance does not hold, and these are all. So, basically this is a time varying system. So, time variant system. Probably the first entry point for you to start looking at time variant systems, because up to now more or less the entire DSP was based on time invariance, and of course we use that part a lot. LTI is very important for us, but the fact that the time invariance has now, time variance has now come in, plays an important role. Okay. So, the second aspect that I want to highlight with the in terms of the upsampler is the following. So, I have the upsampler by a factor of L, and yesterday we also talked about the following, that if we insert a discrete time filter, which is an ideal low pass filter with omega c cutoff at pi over L, then what I get is a system where the spectra, this is limited to pi over L, and then I have the repetition of the spectrum at 2 pi. Okay. So, basically the copies of the spectrum, assuming the input had, if the input was of this form, minus pi to pi, after the upsampling by a factor of L, followed by the filter. Okay. So, the important element in this one is, if we called this as xe of n, basically you have inserted the 0 valued samples. I would like to call this as xi of n. Xi of n, I stands for interpolated, because there are no more 0 valued samples, all of the samples are non-zero, interpolated signal. Okay. So, if x of n, your input signal, corresponded to a continuous time signal xc of t sampled at Ts, then xi of n corresponds to xc of t sampled at Ts by L. Basically you are sampling it at a faster rate, but that is only with the low pass filter that is present. Okay. So, the combination of these two has got a name. This is what we call as a digital interpolator. Notice that I did not go to the continuous time domain at all, but I still talk about something called interpolation and the sampling rate being changed and other things. Where is the underlying framework? The underlying framework basically lies in the box that is on the right hand side, which says that if I view my input signal as a continuous time signal band limited, which was sampled at Ts, the output of this combination of the upsampling block and the low pass filtering looks like the same continuous time signal sampled at Ts by L. So, again what I would like you to do is, as an example, just try out the following. Make sure that you are getting all of the axes, the points on the spectra correctly. So, I have an input signal x of n, which has the following spectrum: minus pi to pi. Okay. So, which means that you have to actually draw the periodicity property also shows. Okay. So, this point would be 2 pi, this point would be 2 pi, then I would have 3 pi and so on. So, basically if I take x of n, pass it through an upsampler by a factor of 4, and then pass it through a low pass filter with cutoff pi by 4, minus pi by 4 to pi by 4. Okay. Ideal low pass filter, cut off from minus pi over 4 to pi over 4. This will produce an output which is xi of n, and the spectrum should be limited to pi by 4. Okay. So, basically whatever was the input spectrum, it got compressed by a factor of 4, or in other words, with respect to the sampling frequency, this is pi by 2, 3 pi by 2 pi, and here comes the copy of the spectrum. Okay. So, in other words, you have effectively created a scenario where it looks like a sampling rate, as if you sampled the original signal at a 4 times the sampling rate, 4 times the Nyquist rate, which will produce for you the following spectrum. Okay. Please go through, make sure that you are comfortable with this representation. If I went to the continuous time, then I would have to worry about the gain. But if my low pass filter if it had a gain of 1, that means it did not change anything, right. So, basically I inserted samples, which means I replicated the spectrum, then I pass it through a low pass filter. So, we need to be a little bit careful about the height of what we draw as the spectrum. If you made this 4, which is what will give you a sinc function with the peak value equal to 1. In the time domain, if you want the sinc function to have a value of 1, then this should have a factor of 4, in which case you will end up scaling by a factor of 4. But if so, just be careful about how the filter is specified. Again, it's a matter of a scale factor, but it's very important that you brought it up. Whether you want to normalize it to 1 in the frequency domain, or you want to normalize it to 1 in the time domain, depends on that. That will be reflected in the reconstructed in the output signal. Okay. But just do make sure you verify that the height of the low pass filter, the scale factor will get reflected in the impulse response that you will see in the sinc function, and the factor of 4 in this case will actually give you a sinc function which has value equal to 1.